Hi, come on in. Good morning. How was your weekend? Great. Good. I'm glad to hear it. What'd you do? Anything fun?
I bought stuff.
You bought what? Like what? What'd you buy?
Stuff for my games.
What kind of games do you play? Oh, you play. You were talking about. Do you have a PS4 or a Xbox?
I have a PC.
Oh, okay. You do PC gaming. Even cooler. Even cooler. That's very neat. Michael, who was here earlier, um, he built his own gaming computer.
Yeah, I'm trying to get a new keyboard
Oh yeah?
because I don't like mine.
What's wrong with yours?
Because it came with the PC. Most of them that come with
Yeah.
PC are
Yeah. You want one of the ones with all the cool lights and stuff in it? Oh yeah.
but
Got it.
I spent $60.
Wow, is it your money? Did you earn all that? That's pretty good. How do you earn money? Do you have like a
Every week.
allowance? Just
I graduated from school, and
that's pretty cool.
from my dad, he gives me $20 for cleaning out the filter on the pool.
Oh, that's good. That's important, cleaning out the filter on the pool. Otherwise it gets super nasty, right? So that's all very good. Very, very good. All right, let's see. Would be like person inside of a person in a person. All right, we'll give Mitchell a few minutes. Or this one. I got a little sheet for money this week. I'm good to go. All right. Cool. Well, that sounds like you had a fun weekend. That was good. Yeah.
I have to order it, and it's taking about, for one of the things,
Uh-huh.
take 10 to 14 days, and the
Okay.
other thing, takes 7 to 10 days.
Jeez. That's not Amazon Prime, is it?
No.
We're all pretty much accustomed to Amazon Prime. 48 hours with this.
Website called Epic Drops.
Oh, okay.
It's for
Okay.
my Roblox game.
Okay. That sounds cool. Mm-hmm. Try this again. This one. Bless you.
So when you get it, it'll give you codes, and you redeem the codes in the game.
Aha, that's cool. That's very cool. Let's see if this will work today. If I'm gonna have to touch it every time. Why it doesn't ever want to seem to. Never wants to do the thing.
That's the one that takes over when we have the mixed.
No, it just doesn't want to play. Okay, I'll play with this sometime when y'all aren't here because I don't know what its deal is. It's weird. That's Miss Jackie over there. She's teaching Spanish. That was you were, I think, looking at that class initially, maybe.
Yeah, I didn't know that you were over here.
Yeah, it's weird. It's kind of hard to make it fit. We always try to make it work, but it's difficult when you've got people of different levels and different places. Like if all of my junior lab rats class was ready for Spanish 1, then we could do it. Oh, I'm gonna get a duster. There is a palmetto bug. That's gross. Do you get those too?
I don't know what they are.
I kind of want to see. Gross. These.
Me and my bunny are starting to kind of bond.
Do what?
Me and my bunny are kind of starting to bond now.
Your bunny?
Yeah,
What
because
she?
Albert.
That's right. Right.
Sometimes when I come in my room, he comes out of his cage into his playpen because.
Well, there you go. You wasn't right, was you? Well, good. 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 Stop on because they can get on the floor. There's a bug over there. I was trying to get him down. No, I'm doing very pardon my giant stick. It's a giant stick. And he's still there. Hooray, hooray.
So we tried to get the book and it's supposed to come this week.
Yeah, your mom said.
I don't know. And plus, we tried to also get a portal to see if there's anything we could do and it said that we're not allowed to do or something.
Did you go through the first portal welcome and everything? Did you do all that?
Yeah.
You have a password and everything to try?
Mm-hmm.
And it didn't let you
We
in?
tried to log in, it said you do not have access to this portal or something. I don't know, I think that it's just not nonsense.
Let's try, look, if you can, if we have time in lab, maybe you can try, we can try to look at it together. So let's,
I don't have access to the account.
yeah, no, you should. Your email's correct and your password is wrong.
No, I don't know the password.
You don't know it?
No, it's not my account.
Oh, okay. You have to know it to get in. So let's maybe heard of it. All right. So let's do today, people.
I didn't do one.
Okay.
Because I didn't have it.
Yeah. So we're all catching up still. So I'm giving everybody a little leeway this first like 2 or 3 lessons so everybody kind of catches on. Okay. So nobody's gonna get like really dinged for anything right now. Because just learn and you guys are new. So do you have a book yet? Or you're still waiting for a book? Okay, you're still waiting for a book. And
It's
you're
coming, it's coming.
Did you have the one I was gonna give one? Somebody was renting one. I think it's somebody in the other class. Yeah, it's the other class. I think. Okay, well, we'll figure it out no matter what. So what we're gonna cover today is pretty much what's in that chapter anyway. So we don't really have to, you don't really have to worry too much. It's not like you're gonna have to go back and read the whole thing because it's all here, okay? So when you go to take your test this week, because you have a test this week, when you go to take your test this week, everything that we've gone over in last week's lesson and this week's lesson will be the kind of stuff that's on the test. And if it's not on your study sheet, which I'll show you at the end of the lesson, if it's not on your study sheet, it's not gonna be on your test, okay? Because I tell you what it is, I think are the high points, the important things that you should learn, okay? I don't want to give you like tons and tons of stuff that you don't know which thing's important. So let's talk about mapping, because this is super important. Mapping is obviously, if you're going to talk about earth science, making some kind of visual aid that describes what we're doing is important. So we got a couple different things to talk about when it comes to how we map, all right?
I learned about mapping about this week because I'm doing the geography, world geography.
Oh, yes. Okay. So you probably learned some mapping too. Have you done any geography? No, done anything with a map before? Ever used a map? So the maps that we use today tend to be digital. Whereas like when I was first driving, if I needed to know how to get from one place to another, I had to get out an actual paper map, either this giant book, or I'd have to get out this thing that you fold and nobody can ever fold it back the right way again. That's a joke about maps. Like you have to fold them back and it's impossible. So one of the things that maps cover is topography. So topography is the shape of the Earth's surface. So this has to do with like how high or how low things are. And these things are called contour lines, okay? So when you're looking at a picture like this and you see, do you see where the little circles are? They're totally closed in the very middle. That's the high point. So you can envision this if you're looking down on it, like you're in an airplane, right? And you see those little circles, those are all like the peaks of hills or mountains. And then it'll tell you on a map, there'll be like a legend or something, we'll go over that in a minute, but it'll tell you what the distance is between these contour lines, and that gives you an idea of how steep of an incline or how low of a decline you're dealing with. So when I first moved in here, I got a little worried because do you know what's through the forest there?
No.
Okay, so the Chattahoochee River is right there.
Oh.
All right, so do you know where the lake is
Which
in
way?
relation to where we are? Linear.
Oh.
In relation to where we are, do you know where it is?
Maybe like no, that's not.
Which direction, do you know?
No,
Just like do that way, okay?
I'm like,
And the river comes through the dam the river, so the river starts on one side of the lake and they created our lake here.
I
Here.
hate driving over the dam. just
It's,
thinking
yeah,
about
it's scary. And there's goats everywhere. Have you seen the goats? They have goats out there that eat the grass. Yeah, next time you drive over ask your parents to drive you over the dam to look for the goats. It's pretty cool. So Lanier actually was formed by an intentional damming of the river. They dammed it and they flooded the area that had previously been a town called Oscarville. They just flooded it, and that allowed for a hydroelectric dam. So it produces electricity when they run the water through.
I know, like, it's been made also that, like, if it's not safe to, it's like the most dangerous lake in.
Yeah, it's a strange thing. People tend to just kind of randomly go under the water and not come up in Lanier. And I don't think there's a
That's
good
because there's,
understanding as to why.
that's
So
because there's buildings and.
there are a couple little buildings left. They've
Structures.
knocked most things over. I think if it's anything, it's treetops. But anyway, the river comes this way. So I wanted to check the topography of my house because I thought to myself, well, what happens if the dam fails one day? Like the whole lake's coming this way, right? So I did some measuring by looking at online tools. I could tell how low the Chattahoochee was compared to my house, how steep the hill was, how wide the river would have to be on the other side and from here to get to my house. And it turns out, even if that dam breaks, it's very unlikely there's gonna be water in my backyard, like all the way up here. So that was good. But that's what topography is about, how high or how low things are, the shape.
My house would get flooded.
Would it?
I'm like 5 minutes from there.
So landform. All right, so a landform is a feature of topography. So this is an example of one of the most common landforms. It's something that's very flat land and has low relief. Relief means like the distance between one thing and another height wise. So what do you think you would call an area like that? Do you know what that's called where it's nice and flat? Field, that's a good guess. Yeah, it's actually called a plain. Have you heard of the Great Plains?
Yes.
Yeah, that's in the middle of this country. You have it. And so in the middle of this country is an area called the Great Plains. That's where like back when we were being settled, there were lots of buffalo and right. You've probably seen movies or seen books where they talk about the plains or go out. That's where cowboys rode around, right? So then we also have this one. Now these are cool. This has a high elevation and a level surface. Do you know what that's called? It looks like that. It's interesting, isn't it? Goes up and then it's just flat. That is a plateau. And yeah, we don't have too many around here. I can't even think of an example around here, but there are some of these out towards like the Ozark area and then out where we have more mountains. And you can see kind of where like water cut through there probably, but left this rock formation here. And those are pretty cool. Another word for tableau is mesa. You may have heard of like Mesa, Arizona. That means table in Spanish. And you can see why that would be called a table, right? And interestingly, tableau is the French word for table. So we're kind of close there with plateau. All right, so how about this one? This one's easier. These are high elevation, high relief, steep changes between like one area and another. What would you call something that looks like that? What would you call that, Cal? What is that? It's a mountain. Yeah, ding, ding, ding. All right, here we go. Now we're awake. That is a mountain, absolutely. So our main landforms here are going to be what? It's a plain, plateau, and mountain, right? So that's what we're talking about when we're talking about landforms. Now there's all kinds of littler ones within. But these are big ones.
North Georgia, right?
We are actually in the like the foothill area here of the Appalachian, right, which is right up here. And the Appalachian Trail, a lot of people like to hike, and it actually starts here in Georgia and it goes all the way up to like, I think Maine. It's a long way. Actually, I have a friend who's hiking it right now. He's hiking the entire Appalachian Trail by himself.
I went up Mount Mitchell.
Yeah.
And we had to turn back around. We were like, nope, we're not going right now. Because we could not see more than 10 feet ahead of us.
Yeah.
Not even 10 feet.
Oh, yeah.
There was a cloud.
Hiking in the cloud. Isn't that cool though?
Not when you're driving.
No, not when you're driving. That's true. So elevation. So when we
And
talk,
windy and rainy and the sky almost died.
so when we talk about elevation, this is a word that means the height above something. What do we measure from when we're
Sea
talking about?
level.
Yes, we measure from sea level. Good one, Mitchell. So it's the height above sea level. So sea level is where like the oceans meet the continents, right? And that's as high as the water is going to go. There's a little tide sometimes, but roughly there. So like I was born and raised in Virginia Beach, and it is pretty much at sea level. The highest point in the city where I'm from, this is funny, okay, because you know, when you came to my neighborhood, like you drive a couple hills to get in here, right? And I'm on a hill, there's a hill right there. Like that did not exist where I grew up. So actually, my best friend sent me a picture or video of her daughters sledding this year at what they called Christmas Hill. And I was like, where is that? I never heard that when I lived there. She's like, oh, it's over off Holly Road. Well, Holly Road has like one little hill and a curve. It's like, oh my gosh, it's a real hill. These kids were sledding. I'm not kidding you. The distance was like from here to the end of the breakfast room. And it was probably a 5-foot drop. And that was the best hill they had. It was very sad. It was so sad. It was like all they had. But the highest point in that whole city is this place called Mount Trashmore. And it's exactly what it sounds like. It was the first city dump. And they piled all the trash up and then they covered it with dirt and grass and they made a park out of it. And you can see it from the interstate. It's a mountain made of trash with a city seal on it.
The dirt and grass on it? or-
Yep, it's beautiful. There's dirt and grass on it. There's the big city seal on the front. Now, when I was a kid, they had to drive pipes down into it everywhere because of course the trash, as it starts to degrade and decompose over time, there are microorganisms in there that produce gases when they eat, and the gases couldn't get out. So they had to put little pipes in it so the mountain didn't like explode or crack open or whatever. And it's not even technically a mountain because there's a minimum height for something to be a mountain. It's actually just a hill. So elevation is something above sea level. So relief, when we're talking about relief, we're talking about the distance in elevation between landforms. So this would be, for example, sea level is going to be 0, and then there is the top of a mountain. The distance between the sea level and the top of the mountain is going to be its elevation, but it's also its relief. Now, say you're not starting at sea level. Say you're starting at, 450 feet above sea level. So then you got to figure out, okay, the difference between there and the tippy top of the mountain, that's its relief. So basically the distance between where you are and how far up you're going to go, or where you are and how far down you're going to go, is called its relief. Now, this is how we kind of group mountains together. So your book used an example of the Bitterroot Mountains, and they are part of what we call a mountain range. You probably heard of a range, like there's Rocky Mountains or the Appalachian Mountains. It's a collection of mountains. So there's this collection of mountains together. And it's right here. See the little circle that showed up on the map? That's where you'll find them, okay? So those are the Bitterroot Mountains, and they're a group of mountains that we call a range. That's a small group of mountains, okay? Now, when you put them all together, it's called a mountain system. So in this case, all that together, the Bitterroot Mountains within a bigger group of mountains, we call a mountain system, and that's the Rocky Mountains in this case. See them? So, for example, on our coast, that's on the west coast, but on the east coast, there's an area in like Virginia, North Carolina, kind of comes down into Georgia that's called Blue Ridge, right? The Blue Ridge Mountains. So that would be a mountain range. And it's within the Appalachian Mountain system. And people tend to say like the Appalachian Mountain Range, but really it's a system, or the Rocky Mountain Range. Like I said earlier, really it's a system because there's smaller groups within them. And then lastly, when you put them all together, they call it a belt. So if you look here on the west coast, it goes all the way down, right? You can see that landform all the way down. So that's a belt. Just so you know, that's how they group mountains. So the American Great Plains, a large area of land, that's right there in the middle. We talked about it a minute ago, like with the buffalo and the cowboys were, right? With mainly one type of topography, is an example of what we call a landform region, okay? So this area over here, the mountains, is a landform region. That belt that we saw earlier, that's a region, a landform region as well. We had in the middle here, it's all plains, and it goes from way down in the delta here, all the way up into Canada. We just call that a landform region because it's just this giant, big plains, right? It's very flat out there. Anybody ever, either of you ever travel out there? Ever traveled to the middle? New Mexico. New Mexico has some mountains, some tall ones too.
I went to.
I have too. I've been, that's in my friend's, you know, the neighborhood you have to drive through to get to the little thing that goes up to Sandy Mountain? It's like, there's little houses kind of everywhere, or the big houses kind of everywhere as you go up. That my friend lives right there in that neighborhood. Like her backyard is Sandy Mountain basically. And we went and stayed with her a couple years ago, and you have to ride that little gondola up to the top of Sandy Mountain. That's pretty high up, and there's like a plane crash down in the mountains below you and all this stuff. It's neat, it's a neat place.
It's crazy. The saddest about New Mexico, like all the neighborhoods have bars in the windows, and it's like really ghetto. I'm like,
Yeah,
going
yeah,
further
she
out.
lives in a really, really nice big house, right at the base of the mountain, so we didn't worry about there, but I know what you mean.
My
But-
dad goes to visit family, and he was like, I couldn't even get my shitty razor blades. I'm like, what?
Mm.
We had to lock them up. I'm like, no.
That's crazy. So if you ever travel out there, like if you go to Oklahoma or Kansas or whatever, and you travel out there, it is flat, just flat. And in a lot of places, there aren't even a lot of trees. It's just a plain. It's like it's a savanna, so it's lots of grass. And you can just drive your car and all the roads, if you ever look at like Google Earth or whatever, the roads tend to be these straight roads and then they turn and it's straight because it's going around people's like farm property. But there's none like, around here, there's a lot of curves because you know, we're working with the shape of the land, like, oh, there's a hill or whatever. There's just like a grid almost, really, really flat. Think Wizard of Oz, super flat. So latitude and longitude. So now we're going to chat about this. Have you ever heard of these? You've heard of these? Have you ever heard of latitude and longitude? Okay, so this is how we talk about
My lesson yesterday.
well, then you should be up to date. Where to find things on a map. Okay, so here's some facts about latitude. All right. The lines are known as parallels. So you see all these lines on the earth, we call these parallels, okay? And they run east to west. And they measure distance north or south of the equator. So if you look, you see where New Orleans is? Do you see where it says New Orleans right over there under North America? Do you see that, Cal? This is New Orleans? Right under the A for America. Yeah, the last A. So if you look at the equator, I know. If you look at the equator and you look at the degrees that go up, about how many degrees north is New Orleans? Can you see?
I don't know where north is.
Ah, okay, so north goes this way, usually. In this case, it goes this way. So you have 0 at the equator, then 10, 20, and 30. And if you look at that line that says 30, see how it goes right through New Orleans? So we would say New Orleans is 30 degrees north latitude. If we were going down there in South America, it would be something or other south latitude. So we call these lines parallels because you can see they're parallel to each other, right? You guys know what parallel means? Like this is perpendicular and this is parallel. All right, so they measure distance north or south from the equator. They're parallel to one another. They never touch. They never touch each other. They just make circles. It's like you took the globe and you just chopped it all the way down. So they cross the prime meridian at right angles. Now the prime meridian in this map,
London.
on this map, it's kind of roughly where all the numbers are, but we'll talk about the prime meridian in a minute because it's a longitude. But they cross it at a right angle, which means like this, right? Like this or like this, like that. Can you find it? Like, right?
It's spelled.
Yeah, it's up there somewhere. Yeah. So they lie in planes across the Earth's axis at right angles, and they get shorter toward the pole. The longest is the equator. So how many degrees is the equator? So the number that runs on the equator, how many degrees is the equator? Can you see it, Cal? What's
I
the?
see 0.
That's correct. It's 0 is right. So the equator is 0 degrees. And how many degrees are the poles? You see, Mitchell? 90. Okay, very good. All right. Yeah, catch on. So 1 degree, you'd have to have read this to know it, is about 111 kilometers. Okay. So they're always the same. The distance between them is the same. Now, longitude is different. See how the lines this time go the other way. So longitude, we call them meridians. And remember last time I said kind of where those numbers are running is where the prime meridian is. That's that big red line there. Now, the equator kind of makes sense. You've got north and south poles, and we stuck the equator right in the middle. The prime meridian, we just picked a spot. It's not like there's a magnetic north and south, like east and west pole. That doesn't work. We literally just picked a spot. And because this was done by, you know, fancy British people, they picked Greenwich, which is where it is. It's in Greenwich, England.
Cool.
So, yep. So they run north and south instead of east and west. And they measure distance east or west of the prime meridian. They're farthest apart at the equator, and then they meet at the poles. Okay, so look at that. Do you see how there's more space between 10 and 0? Here, where the equator would be, Whereas up at the top, you see how they're much closer together? Because they're shaped like this, because the earth is round. So if the earth was flat, oh gosh, flat earthers, then they would be this shape. But it's not, they're this shape. You gotta love flat earthers, right?
How do you not believe that the earth is round?
Oh, they have, you should watch some YouTube videos of flat earthers. If you wanna watch something weird on YouTube, they have all of this evidence that the earth is flat, and it's like.
How- So how are we able to go around the world?
Oh, don't, they have, yeah, they have evidence.
Maybe Earth is two-sided flat.
Maybe. So they lie in planes that pass through the Earth's axis. So the Earth's axis is the North Pole to the South Pole. On my globe right there, you can see it. It's where where the pole literally runs through the center of the globe, right? And we think of them as vertical, right? And whereas we think of the parallels as horizontal, we think of the meridians as vertical. So the prime meridian is how many degrees? Do you see? Look at there again. How many degrees is prime meridian? 0 again, right. So the other was 0 north-south. This one is 0 east-west. All right, so all meridians converge where? Do you see where they all come together? Mitchell, where do they come together?
Wait, what? Can you say that again?
Where do all the meridians come together? You see? Can you tell?
Wait, like the line?
All the lines, where do they all come together?
Oh, the north and south pole.
At the poles, right, very good. So they converge at the poles. All right, now they are semicircles or ellipses, whereas the others were just these like perfect parallel lines that kind of circle the globe. Remember we said they were like this shape. And then sorry,
Measured it by minutes.
1 degree, yeah, okay, so 1 degree varies, and its distance can be anything from 111 kilometers to 0 kilometers. So why does the distance vary?
Earth is round.
So where would you find the distance shorter from one to another?
North and south.
North and South Pole. So do you see that, Cal? So if you, like right here, I can show you with my mouse. Do you see how the distance from here to here is much shorter than the distance from here to here? And that's because they don't go like this, they go like this. So at the North and South Pole, the distance is going to be shorter, and at the equator, it's going to be longer. And it's the same 111 kilometers at the pole that the parallels are apart from one another the whole way up. So
I'm pretty sure some people in Greenland don't get nighttime.
they don't, and Alaska too. There are some places, and yeah, there's a couple places in the world where you can live, and depending on the season, you don't get night or you don't get day either, because of the way the Earth is tipped. And we'll talk about that when we get talking about how the Earth is tipped and how it rotates and how it revolves, and how the axis is we're not straight like this in space, we're tipped. And that's why we have seasons, because as we roll around, that tip stays the same. So like when we do this, we'll do this when we get to that sort of thing. But you see how it's tipped. So if I'm the sun and it's going around me, some of these places are going to have more day, and some of these places are going to have more night, depending upon where you are in relationship to the sun. And that changes as the Earth makes a revolution. So here's your trick. This is your trick. Now you see my little sign. This is one that you should get in your brain. Okay. So when you go study for your test or whatever, this is one not only to just look at for your test, but to keep in your mind forever. This is an easy trick to remember.
Yeah.
Latitude versus longitude. So you think of a ladder.
This
Okay.
is the one I learned.
Yeah. You think of a ladder, all right? And longitude, those are the long parts that run up and down the ladder, right? These two, and they go from, basically they're poles. So it's like going from pole to pole, if you think about it that way. They run, if you imagine the ladder standing up and you try to like put it in a map in your brain and think, well, there's north and south. So they run north to south, up and down, just sometimes how we think about maps. And really though, there's no reason. We generally make maps with north at the top of the map based on how you read and south at the bottom. There's really no reason for that except that it's a standard we've decided. We could turn the map any way and it would still be accurate, but all the words and stuff on it would be upside down. That would do no good. So the latitude then are the rungs that make it a ladder instead of just poles. And they run, so you can think east to west. So latitude runs horizontal across the globe like the rungs of a ladder. And longitude runs from pole to pole, like the long edges of a ladder. So if you remember a ladder, that'll do it. You'll have it. It'll stick in your brain. So now we talk about this thing called the international date line. Where's the rest of my stuff? Okay, so it's imaginary, for real. So the international date line is an imaginary north-south line drawn through the middle of the Pacific Ocean, about halfway around the world, close to the 180-degree longitude of the prime meridian, which cuts through, what did I say the prime meridian cuts through? What town? Do you remember? Greenwich. Good job. Greenwich, England. All right, now.
Fun fact, I forget which country, but they changed their time with the international date line, and a lot of people
Yep.
lost their birthday.
Yep.
I think it was
Uh-huh.
it's
There's a lot of little countries that,
29.
yeah.
29.
So here's the thing. So this international date line is this imaginary thing. It's not official, like it doesn't have any force in international law. So when you're talking about like rules, like official rules that we all kind of agree with on this planet, this is one we sort of loosely agree with. It's like, yeah, that's it. So it zigzags a lot. And it does that because there are countries that it runs through. Now, can you imagine? Now the date line, the earth revolves, right? And then you have day and night. And something has to signify when a new day starts. Like, is the sun rising in Georgia a new day for the whole world? You know, do we all decide that this is a day? And that, you know, Gwinnett County is now another day, they're gonna be ahead of us. It gets confusing. So we've made this imaginary line, all right, and that's gonna be our international date line. But imagine if the international date line went right through here, okay, right through the middle, and we are in Tuesday and Mitchell is still in Wednesday. That's a problem, right? So you can't function like that. So the line now zigzags around countries to make it so that it makes sense. So for Samoa, the time jump means that 180,000 citizens, as well as the 1,500 in the 3 atoll UN dependent little islands that are near it, right, will be on the same day of the week as most of their trading partners. So that makes sense too.
Also, Mitchell being Wednesday, we're stuck in Tuesday. Because you said.
Yeah, so we're Tuesday and you're Wednesday.
But you said he's still stuck in Wednesday.
We're stuck in Tuesday and you're in Wednesday.
Is that the
Yeah.
other way around?
Yeah. So the other way around. Yep. So the addresses and change, people have had to change all kinds of things. So it says when the Portuguese explorer Magellan and his crew returned from their 16th century westward circumnavigation of the globe, that's when they went all the way around. That's a famous historical event. They discovered one day had somehow been lost. So they're like, oh, there you go, flat earthers, take that one, right? They lost a day going around the globe. And like I said, this stuff, we'll get into this more when we like really start talking about this sort of business, but know that there's a line here and it's not official. So this lady has a great little quick video about the international date line and how it works. Make sure we have sound. Boop. Go away. Is she not gonna play? Play, my friend.
That's,
There we go.
I literally had the longest day ever.
She's a goober.
Like really long day. Sorry, okay. Watermelon? No, thank you. I don't want watermelon. I was just saying, I had till 3 a.m. to call my boss in the
Samoa, that was a tough.
Yeah.
People had days that feel like the longest day ever, but that got me thinking, how could I literally have the longest day ever? What would I have to do? And then that got me onto the very confusing subject of global time zones, the international date line, and time difference.
You made my day.
Sphere, and it rotates an entire
She's jumpy today.
in 24 hours, which is the time it takes from sunrise to sunrise. Knowing this, we can work out how far the world travels in 1 hour. So if we take our 360-degree rotation and divide it by 24, we get 15. So every single hour, the world rotates 15 degrees. And we mark this using vertical lines of longitude, also known as meridians. And quite handily, this watermelon here have veins will represent those quite nicely.
Mhm.
24 vertical meridians, each one marking 15 degrees and 1 hour's worth of time. It's all very well having 24 1-hour zones on our planet, but we need to start somewhere. And this is where the Greenwich meridian comes in. It marks 0 degrees to the point where time starts, and it runs through Greenwich in London. The Greenwich meridian, marked out by my beautiful red sticky dot, was chosen at the starting point of time, 0 degrees, because at the time in 1884, 72% of the world's commerce depended on seafar, which used Greenwich as their prime meridian. So this is where it will be.
Okay.
It's midday in GMT, Greenwich Meridian time. The sun is directly overhead. However, it was midday 1 hour previously, plus 1 down to the east an hour line. So if I just rotate the Earth backwards 15 degrees, you can see here we find midday on +1, and then rotate to the east 15 degrees, and continue to our -1 line, we find it's not midday till 1 hour later. And this is why we have plus lines of longitude and minus lines of longitude, as the Earth continues to rotate in an easterly direction. As long as we know the location of 2 places on Earth, we can work out the exact time difference between them. LA is 120 degrees away from the UK. If I divide 120 by 15, that's 15 degrees per hour, I get 8. That's 8 hours. So the UK is 8 hours ahead of LA, -1, 2, 3, 4, 5, 6, 7, 8. Now, Stress Maddie called it 3 a.m. If we subtract 8 hours, it was only 7 p.m. in LA. The Greenwich Meridian marks time 0 and enables us to add or subtract hours, so we can work out time differently across the globe. But we need a way of defining exactly when a new day starts. After all, you can't continue to fly around the world in an easterly direction, just subtracting hours as you go. If you would lose days, then that's time travel, which is impossible. Yet, as there are 24 hours in a day, it makes sense for a new day to start 12 hours or 180 degrees away from the meridian line. So if I subtract 12 hours, we find ourselves at international daytime. Now, here we have from 12 p.m. till 12 midnight on a Monday. The moment we cross over, we find ourselves at 1 a.m. on our Tuesday. Tuesday then starts to grow, slowly eating up on Monday as the Earth rotates, until eventually we get to Tuesday, 12 p.m. Now, there's only so much I can show you with a watermelon, so this video with better graphics down there. So the date immediately to the left-hand side of the international date line will always be 1 day ahead of the date immediately to the right-hand side of the international date line. In fact, if you were to go to the North Pole, you could walk around in circles, crossing from day to day. Conveniently, the international date line largely lies in the Pacific Ocean. However, you can see it's not quite straight, as it's been moved slightly over the years to accommodate the needs of the various countries. As I'm sure you can imagine, it can be pretty frustrating for 2 countries to do business with each other when they're only a mere few hours apart but exist on completely different days. For example, over here, these guys could be working or be busy on a Monday and only a few hours away, everyone's still chilling over here on Sunday. But that is exactly what happens with Tonga and American Samoa. Tonga and Samoa are in the same time zone, but split by the international date line. That means when it's 5 p.m. on Monday in Tonga, it's only 5 p.m. on Sunday in American Samoa. But they're just an hour and a half flights away from each other, a mere 552 miles. Therefore, if I spent my entire Saturday on Tonga, I could then catch a plane at midnight and an hour and a half later find myself in American Samoa at 1:30 a.m. on Saturday. I have a whole day again. Technically, my entire day,
Woo! She just stopped.
48 hours.
There you go.
And that's just by crossing the international date line.
That's awesome.
Sorry, watermelon. Okay.
She had a 48-hour day. So types of maps, we'll go over these real quickly. And we've probably seen a lot of different types of maps. So we have projection maps. Okay, this is kind of like you take a picture of the world and you kind of find a way to project it onto a piece of paper. So we have what we call cylindrical maps. And this one you're probably really familiar with. You've probably seen a map that looks like that, right? That's like
I
you
have
took
one.
the globe. Yeah, that's like if you were to take the globe and you were to kind of cut the top and the bottom and wrap it around a cylinder. But there's going to be some distortion anytime you take something round and try to represent it as something flat. You can't go from 3D to 2D without some distortion. So cylindrical maps are projected onto a cylinder. Latitude and longitude lines are then going to be what? Can you tell what that might be? Look at them. How do they relate to one another?
Greenland is way bigger than everyone.
Yeah, right. So they're parallel and perpendiculars. Everything's a right angle, and that's not really how it looks, right? And then the latitude and longitude lines are going to intersect at these 90-degree right angles. So a Mercator map is an example. So that's a Mercator map, if you've seen that. Okay. Now we have conic maps. This is like you went from the top of the globe, projected it like a cone, put it down like that. So they're created by setting a cone over the globe and projecting light from the center of the globe onto the cone. So distances between regions and their primary areas are distorted at the poles. Now this is good for mapping regions that are primarily east-west in dimension, like the US. So this is, the US runs primarily east to west. We're not, north-south shaped like this. We kind of go this way, right? So cylindrical maps are good for that. Now there's the Lambert conformal conic, okay? And this is your well-known type of conic projection. That's just one. So all the meridians are equally spaced in straight lines, which is, converging to a common point, which is the nearest pole to the standard parallels. The parallels are represented as circular arcs centered near the pole. Their spacing increases away from the standard parallels. So pilots use this kind of map. They use these aeronautical charts based specifically on the Lambert conformal conic. And that's because it does a good job at estimating the distance when they fly. So you've probably seen that kind of a map too. Now, if round, may have taken a chunk out and made it into a square map, but that's where it's coming from. And another kind of projection map is, these have different names. It may be called planar, or it may be called azimuthal. Just depends on what you're seeing. So, and now we're going to take the globe and we're going to project it onto a plane. So something flat. So we've gone from projecting it onto a cylinder, onto a cone, and now onto a plane. And this shows the distances and directions accurately from the center point, but it distorts the shapes and sizes of everything. So your east, west, north, south, but your distance between things is messed up. So it provides navigators with an opportunity to find the minimum distance from one point to another. So stereographic is an example, and gnomic. So let's look now at, there's another one, there's pseudo-cylindrical. So you may see a map that looks like that too, right? So here is topographic maps. We talked about this at the very beginning. So these show changes in elevation with these contour lines that we talked about. And they measure steepness. So the closer the lines are, the steeper the terrain. The further apart they are, the more level the terrain. So contour lines form irregular circles and don't end, and do not end random points. So see how these lines just kind of circle and circle around. And remember, we talked about it when they circle, and you get a little tiny circle in the middle, that's going to be your highest point. So there's geologic maps. So these are going to show the distribution of certain things, rocks, minerals, whatever. So if you're a geologist or you work in mining and you want to know where the coal is, or you want to know where the quartz is, this is how you find it. So this is Georgia, and I can't even read, and I tried to find them, what these were. Most of these are abbreviated, and then there's another key elsewhere that tells you what they are. But this is the distribution of specific minerals in Georgia. So lastly, in our last 6 minutes, oh, one more, sorry, bathymetric, I forgot that. This is the kind that is ocean floor. Pretty cool. So let's talk about map legends and stuff like that, and kind of narrow it down and knock the maps out of here. So map legend is going to define features on a map. You've probably seen these before, right?
Are we gonna go over the maps that cover population?
No, not really. That kind of a map is similar to like the geologic map. It just tells population instead. And you can do maps for just about any demographic. There's maps for housing prices. There's maps for population. There's maps for school districts. There's maps that would be like a type of political map. And we're going to talk about those in a minute. So you got your map legends, right? You've seen this before. There's little shapes and things on a map. rather than writing out Chattahoochee Point Park, they make a little symbol for park and then they put it down at the bottom. And then there's scales, there's different scales. So these are our three main types of scales. You got a graphic scale that explains with symbols, where you can see right there, it says 0, 5, 10 kilometers. You got verbal one that puts it out with words. So this map would be 1 centimeter is the same as 1 kilometer. So that's your scale. And then you got fractional ones where it says 1, 2. This is called a ratio, right? When you see a number, a colon, and another number, like in this room right now, if I said the people in this room are the ratio of males to females in this room is 4 to 1. It's 4 to 1. You see why it's 4 to 1?
Yeah.
Because there are 4 of you and 1 of me, right? So that's another way to scale things or show relationship. So here's some ways of remote sensing. Here's some ways we build maps now, whereas in the past we did it a lot by guys that sailed ships and looked at stars and mapped stuff as they went. Now we use some more technical stuff. So there's a device called Landsat, and it was developed before I was born in 1972, and it uses satellites that reflect wavelengths back and forth, and it gives them some idea of what structures are where. There's another one called TOPEX Poseidon that was 1992 to 2006, and it was radar. NASA used it, and CNES is the one of the which European country is it? France? I think it's France. It's their version of NASA, basically. And then we have this thing called C-beam. This is another older one, and basically this guy it shoots sonar, which is sound waves at this is used specifically for the water. So it shoots sound waves down to the floor of whatever body of water you're in, be it a lake or an ocean, and those sound waves bounce back and it tracks the shape of the bottom. Okay, so you know what that'll be interesting to do over there, right? Mm-hmm.
They use that for finding like sunken ships
Yep.
and stuff.
Yep.
And
Be
things.
interesting to do over there at Lake Lanier. I'd love to see that mapped out. That would be cool. So I'm gonna skip this one because we don't have time, but I'll explain it. So GIS, this is a geographic information system. So this is when you combine data. So you take data from satellite map and data from like a population map or whatever, and you combine them. Most of the maps that you see and use today are some form of GIS. There's multiple kinds of GIS. So we'll skip the video, but you can watch it at home. So go on. So Google Maps and Waze. All right. So these are a type of GIS that we call a satellite hybrid. So if you've used GPS before and you've used Waze, so it's GPS integrated with a road map, and Waze in particular has social media integrated. So people add information to Waze, like there's a police officer here, there's a car on the side of the road, and that gets added to your map. So that's all basically combined data from lots of sources to make some sort of resource that is actually really useful. So Waze is super useful because not only does it tell you how to get from point A to point B, it tells you things to look out for on the way. So we can skip that one. So longitude and the chronometer. I'll read this real quick, and that's probably what we have time for. So throughout the history of navigation, latitude could be found relatively accurately using celestial navigation, stars, right? However, longitude can only be estimated at best. This was because the measurement of longitude is made by comparing the time of day difference between the mariner's starting location and his new location. These are guys in ships, old ships that look like that. Even some of the best clocks of the early 18th century could lose as much as 10 minutes per day, which translated into a computation error of 242 kilometers or more. So it's a lot. That's more than the distance between a parallel. That's like 2 parallels plus. That's a big deal. So and also it's the same for meridians if you're at the equator, right? So in 1764, a British clockmaker named John Harrison invented a sea-going chronometer. This invention was the most important advance to marine navigation in the 3 millennia that open ocean mariners have been going to sea. So in 3,000 years, that the people have been going out on boats, this guy came up with the most important advancement. So in 1779, a British naval officer and explorer named Captain James Cook, you've probably heard of him, he used Harrison's chronometer to circumnavigate the globe. That means he went all the way around, right? And when he returned, his calculations of longitude based on the chronometer proved to be correct to within 13 kilometers. That's pretty darn good. I mean, there's some error there. Now, like, you know, GPS satellite can get us down to like what, a meter, a couple meters? But still 13 kilometers, that's 8 miles. That's not bad for in the 1700s, right? So from information he gathered on his voyage, Cook completed many detailed charts of the world that completely changed the nature of navigation. It also completely changed kind of the way people looked at maps and what people thought certain countries and shorelines looked like, right? So in 1884, by international agreement, the prime meridian located at 0 longitude was established as a meridian passing through Greenwich. So it's kind of a history of how we figured out one day to the next day and how to navigate. I mean, these people were navigating with only stars, so it's pretty darn good. No GPS, no nothing. So this is what you're gonna want to study for your test. You don't have to like freak out and take a picture of this because this will be in your resources folder. So in your Dropbox, and I'll put a link in your weekly email to make sure you see it. But in your Dropbox, there's a resources folder, and it will have, random things that I might add to it, but it will also have your study topics, right? And you're going to want to look over the last 2 PowerPoints that we've done in class, but these are the things that are going to be on your test, right? So this is what you'll be looking for when you go to study. And you guys are done, and it's exactly 10:46, so we did pretty well here. All right, awesome. So we can call in Drew. You want to go get your class because it's time for lab. Stop this one. Okay, end the meeting.